I wanted to give you an overview of the different kinds of reactions, which I did earlier on Thursday and posted a couple days ago. So now it's Saturday morning. I'm going to give you an example of each of the 5 basic kinds, just looking at an equation. So here we go. We have double replacement reactions. These are the ones that we did in the solubility lab. So I'm just going to make up some examples. So suppose we had some barium chloride, and we combined it with potassium sulfate. Notice how you've got a compound and a compound. See, compound, compound. The cations change partners. What are the cations? Barium, potassium. So I'm going to have barium going with the sulfate, and potassium is going to go with the chloride. So plus potassium with the chloride. You'll also notice that I carried over this 4, didn't carry over the 2, didn't carry over this 2, and the reason for that is that only the subscripts that are part of the polyatomic ions will carry over to the other side. That's because this 4 is actually part of sulfate, so it has to carry over. So on this side you check your charges, +2, -2, and then potassium is +1, that's -1. So it looks like those formulas are okay. And then to balance the equation, you'll notice there are 2 Ks and 2 Cls here, so I'm going to have to put a 2 in front of the KCl. Like that. So there's our balanced equation for a double replacement reaction. Once again, you notice that there are 3 steps. What was the first step we did is write the combinations down. Then we write the formulas correctly by using charges and subscripts. And then we balance the equation by using coefficients. So I'm going to put here C and S, which stands for charge and subscript. And here I'm going to put coefficients to remind you that you have to put the big numbers in front. Remember, the big numbers can only go in front of complete formulas. They cannot go in the middle of the formula. They can only go into places that I underlined. All right, the next type example is single replacement. I gave you a couple of examples of those in a previous movie. Notice here that it says the single element must be more active than the element that it replaces. I included over here an activity series of metals. So if I had, for example, K plus NaCl, K would replace, since the single element can form a cation, is going to replace the sodium. So single element can form a cation, replaces the sodium because that's the cation. So I'd have KCl, and an Na would be kicked out. Checking our charges here, this is +1, that's -1, so that's good. And this is just zeros by itself. So that one that's actually complete and balanced as it stands. I want you to notice that K is more active than Na. If I had Na plus KCl, there'd be no reaction because Na is not active enough to replace the K. So the things that are, if this reaction type occurs, there has to be, the single element has to be more active than the one underneath it. And I will not make you memorize this activity series, so you'll be able to use that. All right, then the other type of single replacement would be like bromine and say aluminum iodide. I just make up one here. If we, since this element is a anion, potentially an anion, it's going to tend to gain electrons. It's going to replace the iodine. So what happens is the aluminum combines with the bromine, and the iodine is replaced. And remember, iodine is part of Brinkelhoff, so it has to occur in pairs. The aluminum is +3, -1, so you got to put a 3 down here. Have you noticed that the first thing I did was write combinations up here? Second thing I did was write the formulas. I just finished that using charges. Incidentally, a reminder that the charge on any element that's by itself is 0, so you don't have to consider charges writing this formula. All right, so now the equation is, all the formulas are right. We have to balance it using coefficients, and coefficients have to go in front. They can only go here, or here, or here, or here. So you look, you got 3 i's, you got 2 i's. So you have to find a common multiple of 2 and 3. So what is that? Oh, 6. So we put a 3 here. I'm going to put a 2 here. Then that creates a side effect of having 2 aluminum, so I have to put a 2 here, which has a side effect of making how many bromines? That'd be 6. So on this side, I'm going to need to put a 3 to make everything equal out. All right, now in this next section, we're going to look at 5 different kinds of decomposition reactions. And the first one is a metallic carbonate. So you'd have to know what carbonate is. And you might look at, say, we'll do sodium. No, we'll do aluminum carbonate. Okay, so we'll have aluminum carbonate. All right, so I'm just creating one. So aluminum's +3, carbonate's -2, so it'd be a 2. Whoops. You'd have to put a 2 on the right there, and you have to put a 3 right here. Now our combinations, metallic oxides and carbon dioxide, so which of these is the metal, the aluminum, the carbon, or the oxygen? So it'd be aluminum. So you put the aluminum there, and oxide would just be O. And then carbon dioxide, C. What's di mean? Di means 2, so it'd be 2 oxygens. All right, so you'd have +3, you'd have -2. So you put a 2 here, put a 3 there. 2 times 3 is 6, 2 times 3 is 6. So now we've done our combinations and our formulas. We need to balance. We've got 2 atoms of aluminum, we've got 2 atoms of aluminum, but we have 9 atoms of oxygen here and 3 atoms of carbon. Let's just do the carbon first. General helpful hint, if an element appears in 2 different places on the same side of the equation, leave that one till last when you balance it. So do the carbon first. So you got 3 carbons, so you put a 3 right in front of the CO2. And that then has a side effect of making 6 oxygens here. Oops. There was a 3 there, plus, remember that? I accidentally erased that. So it has a side effect of making, when I put that 3 there, it gives you 6 oxygens here, plus these 3 makes 9, and over here 3 times 3 is 9, so we're finished. Okay, a metallic chlorate. Suppose we had potassium chlorate, just taking a random metallic chlorate. Now you're going to have to recognize that a chlorate is a ClO3. It's going to make a metallic chloride and oxygen. Is oxygen part of Brinkelhoff? Yes. Okay, so that's your combos. +1, -1, so the charges are okay. All right, now we need to balance the equation. We've got 3 oxygens, you got 2 oxygens, so common multiple. 3. Now you can only put numbers in front, so it has to go there. When you put a 2 in front of the potassium chlorate, it creates 2 Ks and 2 Cls, so you have to put a 2 over here, and then that one's done. Okay, metallic hydroxide, we'll put aluminum hydroxide, and put parentheses here, and we got a metallic oxide and water. So let's see, put a 3 there, yields. A metallic oxide would be Al and O. Pardon me just a minute. I have a Great Dane puppy. There you go. Okay, so you got a metallic oxide and water. Oops. Okay, so the metallic oxide would be aluminum and oxygen plus water is H2O. All right, so formulas, we have a +3. We have a -2, so you'd have to have a 2 and a 3, and that's good. And water is good, of course. So we have, remember how I said a minute ago that oxygen shows up in 2 places, that you should leave it till the end. So I've got 3, I'm going to leave the oxygen. So I got 2 ALs, I got 1 AL, put a 2 over here, and that multiplies this whole formula by 2. So I end up with we got 3 oxygens here, times 2 is 6 oxygens, but once again, oxygen is in 2 places, so I'll leave it till the end, but remember there are 6 here. And then there are hydrogens on the left side, and hydrogens, there's 2 times 3 is 6, so over here is 2, so put a 3 there to make 6. Now look at the oxygens, 3 here, and 2 times 3 is 6, so we're balanced. Okay, pardon me, I'm going to move my puppy out of the office here. All right, now back. All right, acids. We've got non-metal oxides and water. And these are the most complicated of the basic reaction types, probably. Acids and then synthesis are a little tricky as well. So acids, we'll start with something like, say, phosphoric acid. All right, so it's going to make a non-metal oxide in water. All right, so the non-metal oxide will not be the hydrogen because the hydrogen is going to go with the water. So the non-metal that we're talking about would be the P that is in the H3PO4. Okay, so I'm going to take that P and put it with oxygen on this side, plus water. So far that's not very complicated. Here's what's a little tricky. We're going to assume that the oxidation number of this P is the same as the P on this side. So we've got to figure out what that oxidation number is. All right, we know that this whole compound has an oxidation or a charge of 0, because that's the idea of a compound, that the charges all add up to equal 0. We know that oxygen is -2. We know this whole PO4 is -3, by the way, in case you're confused by that. So this whole PO4 thing, in parentheses, is -3. All right, so -2 times 4 is -8. +1, for hydrogen is +1, times 3 is 3. So -8 plus 3 is -5. So what does the P have to be in order to make the whole thing equal 0? So it's like 3 plus x plus -8 equals 0. So what is x? Well, x is 5. So this we're going to assume stays at +5, making, and the O is -2, so it'd be P2O5. And then it becomes easy again. So you've got 2 P's on this side, you've got 1 P over here, so you're going to put a 2 there, which gives you 6 H's. So you have to put a 3 over here, and we left the O's till the end because they appear in 2 places. So 5 plus 3 makes 8, 2 times 4 equals 8. Now alternatively, you could have figured out the P by using this technique. It's another way to do it, kind of like in a computer. There's more than one way to get to the what you're trying to accomplish. So the PO4 we know is -3. So the oxygen is -2. 2 times 4 is -8. So -8 plus x has to equal -3. So again, x equals 5. All right, so either way works. You can consider the ion by itself or consider the whole formula. As things get more complicated, it's easier to consider the ion by itself. Okay, and then the last type of synthesis is just straightforward individual elements. These are pretty easy. So Na, suppose we had sodium and chlorine. It's going to make NaCl, and Na is +1, Cl is -1. So that's right for formula. Balancing, 2 Cl's, 1 Cl. You got to put a 2 here. That gives you 2 Nas. Got to put a 2 over here. Now you're finished with the decompositions. All right, I'm going to come back and do these last 2 examples on different movies to avoid getting them too long. So, be back in a minute.